everybody, for another episode of AGR Breaks It Down. My name is Brandon Aldinger, Senior Scientist here at American Glass Research. Usually I'm in the other stool, but this time I'm happy to have with us Phil Ross, who is here teaching our Batch and Furnace seminar at our Butler, Pennsylvania location. Phil has been in part of the AGR teaching roster for years. He has his own business of Glass Industry Consulting International and has been doing this longer than I've been alive. So with that, we're going to be talking about Phil about a number of different batch and furnace type of questions, as well as just some of his experiences that he's had over the years. I think it'll be really fun. So Phil, maybe you could tell us a little bit about how long you've been in the business.
Well, I ironically was recruited out of high school by the glass professor at the University of Illinois. I grew up in that same town, and he was a family friend of my parents. And so he convinced me to go into ceramic engineering, which I got my degree in 1965. And for some reason, I ended up choosing glass as a ceramic material that I chose to go into, and I've worked in this industry ever since, really directly with glass manufacturers for 27 years, and then did independent consulting from that point forward.
I think you said it was 1960.
65 is when
65.
I graduated.
Okay, great.
Yeah.
So it's been a while. And how many furnaces and plants do you think you've been in that time frame?
That's a good question. That's a real good question. I have to think about it. I mean, when we built the last furnace I was building as part of a manufacturing company, that was factory number 127 in the United States. We only now have just over 40 in the container industry. And I would say 90% of those factories, for one way or another, I had a chance to visit and maybe learn something about.
Great. I've got a list of questions here. We've looked at them beforehand, but we really haven't talked about them. So I'm going to be very interested to see what your thoughts are on some of these issues. So the first question I had was, kind of give us a historical perspective on furnace lifetimes. Mm-hmm. So how long were furnace campaigns, or the life cycle of a furnace, when you started in the industry, and how does that compare to today?
Okay. Yeah, good question. In fact, in the class today, I showed a video from 1939 of a factory in Ohio. And in that video, they talked about the furnace life was 12 months.
Oh my gosh!
And then when I got in the industry in 1965, the typical furnace life, and it would vary a lot, would be about four years.
Okay.
And this is campaign life, meaning it's cold, you heat it up, you run for the campaign lifetime of this example, 4 years, and then it's time you got to take it down cold and do something with it. Some companies would intentionally have shorter cycles. Some companies would shut down every 2 years for Christmas and take advantage of that. And others would find ways of extending life, as we all do now. And the average life in the early 1990s for container furnaces was up to about 7 or 8 years calendar-wise. And presently we're talking 12 to 14 years for container furnaces. The flat glass furnaces similarly are actually going over 20 years now.
Over 20 years. Wow.
So it's a nice time in a way, but also there's a lot of things that have to be done to keep these furnaces operating.
Maybe not so great if you're a furnace manufacturer, but what are some of the major technological advances that made that increase possible?
Yeah, it was quite a list. I mean, obviously, the materials subject to the life of the furnace include the refractories. And so we've had improvements in the type of refractories available that can last longer and operate at high temperatures. We found ways of more effectively using insulation. So it means that we can make more glass per day because holding more heat in to do melting instead of losing it to the atmosphere. But design changes of the combustion system have been a major issue. We've gone to different types of more efficient flames, the use of electric boosting, batch wetting, and something I never want to forget is how good a job we learned to operate the furnace, because a lot of the life of a furnace really involves how many times you've gone off standard.
Oh, what's off standard?
Well, you can have power failures, raw material upsets, any combination of things like that. In the class, a couple of students had issues recently with power failures and
Mhm.
other issues interrupting production. And then the way you handle those interruptions can have an impact on ultimate life.
So I guess it's a little bit like in when people talk about cars, they say that if you just ran your car at highway speeds and you never like started and stopped, it would basically go almost forever. But it's because you have to start and stop, and driving in cities is a lot rougher on the car. So it's kind of like that with furnaces, where starting and stopping is rougher on the furnace and degrades the lifetime.
I think to some extent, yes, because if you look at the most successful furnace campaigns, they're dealing with what are called patch shops, where you're making only a common-sized beer bottle all the time or wine bottles. Where if you're into the fresh food pack type of things or wide mouth food containers, you're going to have many more changes because of not only the nature and the pull rate required for those products, but the fact you have to operate in different temperatures.
Okay. Cool. So, how do you know when it's time to end a campaign? It's time to start shopping for a new furnace.
Well, sometimes the furnace will tell you. So the end of the campaign is interesting because when I meet a new company and they ask about their furnace life, they'll usually quote a number of years or tons produced. But then the question is, what shuts you down? Is there an issue with a component of the furnace? Is it a business lull? Because sometimes the flow glass industry will take advantage of those business cycles and choose to shut down then. So it's really varied by a lot of factors. The furnaces have different components that impact the ultimate life. There are weak areas that will result in glass leaks. The combustion system with the air-fired furnaces can have a refractory deteriorate and plug up, and you get the equivalent of emphysema. The furnace has trouble breathing. And so to some extent, that's going to dictate the length of the campaign of the furnace. And hopefully what you've done is planned and predicted for when this is going to occur, so you're in a position to have the replacement refractories ordered and ready to go when it's time. And the difficult ones are when the furnace has decided to stop running, mostly by glass leaks.
Okay.
That's the tough one.
What are some common ways that people try to squeeze out like an extra year or so of furnace lifetime?
That's one of the major innovations really in the last about 20, 25 years, where we have a lot of newer hot refractory maintenance techniques, and this include such things as ceramic welding, where we can have water-cooled devices go inside the furnace and build up a layer of refractory to replace what is worn. It's not as good as original material because it's a sacrificial layer, but you can do that multiple times and extend the life of the furnace. We certainly have overcoating, external coatings of monolithic castings, overcoat blocks, etc. And I think those are the most major ones.
Okay.
Obviously, in today's world, too, we're relying upon more and more recycled glass, and a higher percentage of cullet has its own contribution to longer furnace lives.
Is that just because you can use lower temperatures, or
and
less
also
soda?
all the above, because the cullet doesn't have the dusting potential of some of the other fine ingredients, and the wear of the superstructure refractory is really determined by how many chemicals from the glass making process end up getting on those refractories. It may get on them as a vapor, which is unavoidable, but someone has to do a dusting, firing practices, etc. So everything we can do to keep the glass making chemicals only in the melt process is going to extend the life of the furnace.
Okay, great. So if we talk about trying to extend furnace lifetimes, obviously sometimes people can push it a little too far and it doesn't work out. So without naming any names, I know you've seen a lot of things in your years. What is one of the worst furnace disasters you've ever witnessed?
Can I only choose one?
Well, go ahead. If they're
if you talk about glass leaks, first of all, there's a couple of different categories of things. One is the furnace is operated longer than the lining of the molten glass allows, and so you have a leak, and it can be minimal that you have a chance of containing, but in many cases it's a catastrophic leak, and all the glass leaves the furnace, and hopefully you contain where that molten glass goes, because you're talking hundreds of tons of glass that 2,600 degrees Fahrenheit or so.
Have you ever witnessed that in person, or have you only kind of seen it afterward?
Do you see my gray hair? Sure. I've been on site when a few really bad leaks occurred, but most of them I've come in to see the consequences of it.
Okay.
And the consequences are kind of varied, because I can think of a couple of examples where there was an operational upset and not the furnace being old. And this has to do with conditions where you have a foam developed during a color change or other upsets. And that foam can actually come out of the furnace and melt the binding steel.
Oh, really?
It releases the hydrostatic
Okay,
hold
yeah.
on the molten glass.
Right.
And unfortunately, I've seen that in a number of furnaces, both, or more overseas than here, but we've had them every place. So,
Right. So is that the worst? What's the?
Well, I think the other episode, I can think of two examples where there was an operational error, and in a variety of ways, the furnace was overheated and dramatically melted out the crown of the furnace, and actually holes came open as large as our desk or eventually this room, and you had to shut the furnace down. So the furnaces were not necessarily that old, but there was an operational variable.
Okay, so the crown collapsed. They got holes in the roof.
Yep.
When that happened, are they toast, or do they try to repair those things?
They're toast. In fact, both instances I can think about, they had to be shut down cold and rebuilt. One furnace was literally less than 6 months old. Another one was only 3 months old.
That's $1 million oopsie there, I guess.
It's a lot more than that now.
Yeah, it's true.
Yeah.
Okay, now we're going to switch to another glass tech type question. This is a question I get a lot, and I kind of have an answer that I give, but I'd be interested to hear what you have to say. Sometimes people have problems with seeds. Glass producers, seeds are just another term for bubbles, and they are gaseous inclusions. There's nothing inside of them. They're hollow, and a glass manufacturer will say, hey, I've got this seed or blister. What caused this blister? What are some ways to answer that question for them, or how might you go about trying to determine that?
Sure. Well, the more traditional seeds relate to what's called the refining process inside the melter, where we have some raw materials like soda ash and limestone that automatically lose almost half of their weight as carbon dioxide. And so in the melting process, those gases are sort of trapped in the first glass made. And depending upon the size of the bubbles, they may or may not have time to rise to the surface and break away. And so you'll have inherently a certain amount of remnant bubbles of a smaller size, which we call seeds. Those relate to a combination of things. Time and temperature is one issue, but the way in which we have what's called chemical refining, where we accelerate the rate of removal of the bubbles with a variety of means inside the batch formula.
Can you make any conclusions by saying, okay, I see a really small seed, therefore it's due to bad refining, or is that kind of not a valid conclusion?
Well, unfortunately, you may have multiple suspects.
Okay.
And so a great analytical tool available, well, we've had it available for a long time, is we can take samples of those seeds or bubbles, or if they're larger, we call them blisters, and we have them sent to a laboratory that can measure the actual chemistry of the gases inside those bubbles, as small as less than half of a millimeter in diameter. And the chemistry will tell us something about the potential origin. Now, as example, if argon is present, it means the air somehow is involved.
Okay.
If it's high in sulfur, you have to look at batch chemistry issues, et cetera. The other thing that is interesting is that as part of that analysis, we can also get a indication, semi-quantitative measurement of the internal pressure of the gases inside the bubble. And the interesting principle is that when we create a bubble, wherever it may be, in the melter or downstream in the forehouse or whatever, the bubble is created, and depending upon, to some extent, what the gas is, but more importantly, how long it's existing in the glass, some of those gases actually want to disperse into the glass structure.
Okay.
So the internal pressure, in an inverse way, tells us how long it's been since the bubble formed.
I see.
So bubbles from the melter, where we think about furnace temperatures or batch lines or optimizing of refining in process in the batch will be at much lower pressures than bubbles that are generated downstream in the working end of the forehearth or even the gob feeder. In fact, we had one example in the class today of an analysis of a bubble in a container, and it was air. It was nitrogen,
Right.
oxygen, and argon, and that actually ended up being trapped air in the process of loading the glass into the light bulb.
Okay, so all the way
Now,
back.
that's more unusual, but it just shows the power of getting that analytical information of both chemistry of gases and internal pressure.
So let's say we have a really typical scenario where a glass plant exceeds their seed count. They got a lot of little tiny seeds in there, and well, a lot meaning more than they're supposed to have. What are like the top 3 to 5 things you'd say they should check first?
Well, you want to look, first of all, at your refining mechanisms in the batch. There's a property called redox, and that inherently has an impact on some of the refining aspects in the furnace from a chemical point of view. You also have temperature involved with the extent to which as yet not refined glass can get near the exit of the furnace. So you have parameters to look at in the furnace like batch line perhaps, or a lot of key temperatures that will tell you that possibility. Issues of the scheduling of energy input. In today's world, that's not just how much gas you're using and what temperature you're running in the supercharger of the furnace, but also how much electrical boosting you're using to have energy release on the bottom of the batch piles, which accelerates the melting process and therefore refining.
Okay, good. That's all I had about seeds. And let's switch to something kind of related, stone analysis. So first question would just be more of a fun one. So I've been doing stone analysis at AGR for a while. We have a book on that. But occasionally I get stories about odd stones that end up in furnaces. And we typically you hear about, okay, we did a furnace repair. There's some nuts and bolts and things that got accidentally thrown in the furnace. That's not too unusual. But I have heard of a case where there was a cold repair and someone had actually left or thrown in a jackhammer into the furnace that had just been completely melted because glass is way hotter than the melting temperatures of metals. And so that ended up being a lot of steel that got inside the actual glass bottles eventually. Another story I heard more recently as a stone class was kind of a funny one. This had to do with a person in the stone class asked me, saying, what happens if what kind of stone would a cell phone make if it were in the furnace? And I was like, what are you talking about? How would a cell phone get in the furnace? Well, it turns out he had a colleague at the glass plant, and this colleague had this coworker had a cell phone, and he got some sort of spam message on it that said, like, this phone has been compromised. If you see this message, then you have been hacked, and you need to click this link to whatever. So a common spam message. Well, this guy got freaked out, so freaked out that he actually threw the phone into the furnace. And I guess hopefully he was up for renewal on his contract or something. But that phone is toast. Definitely made some kind of stone, but I don't know. A lot of it would burn up circuit boards, but there's glass and steel and who knows what else in there. But I was wondering if you've heard any really unusual things that have been thrown into a furnace.
Well, answer this in two phases. First of all, anytime you rebuild a furnace, you think about things like jackhammers being left in there, and all the furnaces that I was ever involved in, knowing that ultimately I would be the responsible party, I would always do a physical inspection inside the furnace before we seal it up for the heat up. And this included going through the throat, hopefully bringing some other people, the production people, in to show that we had everything clean, that there's no mortar, which might be a stone on startup, seeds, et cetera. And there were a few oddball things. Sometimes a piece of plywood had been left in the regenerator, which would catch fire halfway through the heat up, and we wondered where the smoke was coming from.
Okay.
But we tried to avoid that as much as possible. In terms of stuff.
Sorry to interrupt, but do you actually crawl through the throat of the furnace?
Yes.
Oh,
you do. You look like a caterpillar crawling. You're looking upward and doing what do you call it?
Knowing the worm, like from cancer.
There we go. Yeah, and I think I could still fit through a throat, but I don't know if I want to that much anymore. But in terms of stuffing getting in the furnace, I mean, obviously we do have ongoing contamination questions of mold equipment or tramp metal.
Sure.
We have magnets and non-ferrous metal detectors to try and stop that. But in terms of the craziest thing, I was not involved in this, but I had hired an engineer who is originally from England, and he said that on the night shift in this factory, they used to catch mice and rats.
Okay.
And guess where they ended up?
They throw them in the furnace?
Yeah.
Well, they probably wouldn't make stones or any kind. This would burn right up. But.
No, they said it was a very interesting explosion that occurred.
Oh,
I don't mean morbid, but that's the most unusual thing I can think of.
Burning rat smell may not be the best, though. I'm not sure that would be fun. Okay, so that kind of answers that question. So another one that is probably the top batch and furnace question I get, at least regularly, has to do with cat scratch cord. So just if you're listening to this and you're not familiar, cat scratch cord are the very faint streaks that look like parallel scratches on the side of a glass container. They're on the exterior surface. They are a type of inhomogeneity in the glass and usually can only see them in reflected light. For a beer bottle, not a big deal. But if we're talking about a fancier bottle, like a nice liquor bottle or a cosmetic bottle, then companies get more concerned and they got to get rid of them. So then I get asked, how do we get rid of this cat scratch cord and what are its causes? Mm-hmm. So I was hoping you could tell me a little bit about how cat scratch cord is created, and then we'll look at how you might get rid of it.
Sure. And there's been an evolution of thinking on this. I remember it was such a big issue back in the 80s that one of the furnace design companies sponsored a seminar to talk about cat scratches, their origin, and potential solutions. And there were like 35 companies that came to a meeting in Pittsburgh years ago. But the short answer is that the material that makes a cat scratch is a remnant of an erosion corrosion product of the refractories back mostly in the melter of the furnace. And so it's analyzed as having high aluminum, high zirconia, and it is heavier than the glass, so this runs down and sinks to the bottom of the furnace, and under various conditions it's pulled across the bottom of the furnace, and the glass flow goes up in the forehearth as a streak and becomes a cat scratch in the gob. So the major variables to try and get them better operationally, if you have them before you can make changes in the design of the furnace, primarily involve putting what are called T-bar blenders in the forehearth to try and break it up. There is a system of a bottom drain in the forehearth, which I have seen a number of, and I don't think they're near as effective as the T-bar blenders are. But getting back to how to solve the problem, we've looked at the types of refractors we want to use in the forehearth and working on. We've gone through that transition, which has helped a little bit in insulation. But the most major variable that I have is the design of the throat.
Oh, really? Okay.
I had one client. I was not involved in the design of the furnace. It was built, a very modern furnace, and started up, and we had cat scratches. And they were building another furnace in the factory, the same size, same pull rate, same glass, etc. And we chose to discuss an alternate design in the throat area that was put in that design, and that furnace started up with everything else the same without cat scratches.
So throat design.
And then their next three furnaces, they use that same modified design in those furnaces, and they don't have scratches either. So, if you have it before you have a rebuild, you got to live with it, and that's why the blenders in the forehearth may be an option for you.
Sure. So you had mentioned that it's coming from the melter typically. Now, is that going to be from above the melt line or typically below the melt line that we get the erosion?
It's actually all the above, depending upon how much superstructure rundown you have, which is worse with drier batch, better with wetter batch. You have fusion cast refractories that are being eroded by that dust, and it's going to run down into the glass. The more major source is what's called the metal line cut on the sidewall blocks.
Okay, right.
Because that block wears a lot the first year or two of operation. In fact, of 10 inches, it'll wear 1 inch in less than 1 year. But as it progresses back further, it doesn't wear as fast. So early on, you're dumping more and more of this product into the furnace, and this is why the cat scratches are usually worse early in the furnace campaign and the best at the end of the campaign.
Mm-hmm.
So unfortunately, what happens, you think you don't have a cat scratch problem anymore. You rebuild the furnace, not making other modifications, and lo and behold, you're back again to square one, and you've got a cat scratch problem.
So you mentioned that also improvements in Vorhoff refractories help to limit the cat scratch. But
yeah, it helps to some extent, and what we've done is we've looked at the corrosion rate of the refractories in the melter, which are at very high temperatures, mm-hmm. and there's a preferred composition using aluminum, zirconia, silica in those areas. But at lower temperatures, ironically, the high aluminum fusion cast is more corrosion resistant than AZS, mm-hmm. and so that refractory is preferred in the working end and the Vorhoffs. And then in the Vorhoffs, some Vorhoffs are going with a bonded high alumina refractory as well. Mm-hmm. And that's another, the corrosion resistance at the lower temperatures is more than satisfactory. So.
Okay, so usually you aren't going to get the cat scratch from the Vorhoff. It's mostly the melter.
Yeah, it took us a while to figure that out.
Sure.
We really thought that it did have an effect because, ironically, changes in pull rate and changes in some of the temperatures in the working and entering the Vorhoff seemed to have an impact on the cat scratch. But all that was doing was changing how much of the bottom glass was contributing to the total glass going to production.
I think sometimes when I've analyzed it, I have seen one or two cat scratches where I just saw alumina and not zirconia. Could that mean it is coming from the Vorhoff, or is it just
no, I don't
strange?
Think so. I don't think so because if you look at fusion casts, it's not a monolithic chemistry.
Right.
It's built up with crystals of alumina. There's nodular zircon crystals inside there as well. And then a surprising amount of the chemistry is actually a glassy material, a non-crystalline material, which we need to have some of because it gives us a buffering of thermal shock resistance. But that glassy material is really the culprit that's going to come out in a variety of ways that varies how much is polluting, if you will, the bottom glass on the furnace.
Okay. All right. So that, I think, covers cat scratch pretty well. Let's talk a little bit about just general glass industry things. If there's one piece of advice, let's say you got a new batch and furnace supervisor or batch and furnace operator who's just entering the field, just joining up with some glass company. Could be float glass, could be container glass, whatever. What is like the best piece of advice you could give that person?
Well, they're going to come with some kind of a background. And when you talk about going into a manufacturing environment, you're going to have to accept that this is a 24/7 operation. And so that's going to mean that you're going to have an ongoing relationship with the manufacturing process. And I think depending upon the background that you have by interest or education, you're obviously going to have to build upon that. And the way in which you gain knowledge is going to come in different ways. I remember graduating with a degree about glass and going into a glass factory. Someone said, son, you're going to now really start to learn how glass is made. And they were absolutely right. There's the idea of the theory behind things, but you've got to get a practical side to marry with that. And so the more exposure to people that can expand your base of education and break down misconceptions, which is still a big problem today. People have misconceptions about things. I think the sooner you'll get on track with everything going the right direction.
What do you think are maybe the top couple misconceptions that people have when they get into batch and furnace?
Well, I think first of all, the primary objective of the batch and furnace area is you are servicing a production department. You're making the necessary quantity of glass in a quality state or chemical state that you're supposed to have, and you're going to be doing it in a way that is minimizing variability and being stable in what's going on. So this always goes to tighter ability to have good glass quality, minimizing temperature ranges that would have a downstream effect, et cetera. So I think that's a big factor. If that answers the question.
I was asking about it. Are there some, I guess you could say, some lore that's really incorrect, but you've seen it at a lot of glass
Oh
plants.
yeah.
What are some of the
Well,
top ones?
I think, and this has been it's been going on forever, and this is the age-old workability
Okay.
issue.
What's that about?
Well, you have in a manufacturing plant, let's say it's a container, you have a batch and furnace department that is making glass that's going to go to a fabricating operation. And there are different departments with different leadership and different perspectives on things. And so if you are making the correct glass chemistry all the time with everything we're doing with raw materials and weighing and issues with getting things melted into good glass, that chemistry of the glass has actually fixed all the physical properties. It's a material, and chemistry dictates physical properties. So such things as temperature versus viscosity, which is a major factor in fabrication, that's pretty well locked in by the composition. But in fabrication, you're trying to increase the viscosity of the glass as it's cooled down very, very rapidly. If you think about making a beer bottle, that gob is going to start at about 2100 degrees Fahrenheit, and the surface of the container coming out of the IS machine is less than 900 degrees Fahrenheit, and that's been accomplished in less than 8 seconds. So there's a lot of cooling that's going on, and the issues with variability of fabrication results really relates mostly to how we are changing what's happening with the cooling of the glass in fabrication. So it's heat extraction device. How do we lower the glass temperature in fabrication? We lower it by the contact of the molten glass or fluid glass with metallic molds that are a lot lower temperature. We lower the temperature by blowing compressed air and blower air on the glass. So that's the major part of the heat extraction on the glass. But the other area that the glass does contribute to is the fact that we're relying upon the heat losing temperature by radiation. You walk by an IS machine and your radiator indicators tell you there's a lot of heat coming out here by radiation. And in the case of the glass, we do have one chemistry component that can vary that, and that is the ferrous iron. And so the final objective to get glass variability out of the equation of production difficulties is the assurance that we're maintaining a stable redox or ferrous iron level in the glass. And then beyond that, it's really a matter of trying to understand the variability of how the glass temperature is reduced in that 7.5 or 8 seconds.
Okay, so is the misconception that the workability problem is because it's something happening in the furnace? But you're saying it's really just the composition that's setting that, and then the temperature decrease.
Yeah, it's really both, because what you'll oftentimes hear is you've got there's a production problem. Let's change the glass composition, and the old jokes used to be let's add 5 pounds of soda ash, and I fought that battle the majority of my career.
Because soda ash is supposed to make it more.
Well, it changes the temperature versus viscosity curve, and so some people choose to go that route. I have one client that the only reason we change the glass composition is because they're in a very hot area of the world, and there's a winter-summer requirement to change things because we cannot cool the glass as easily in the summertime at 50 degrees C, and we can cool it a lot easier in the winter. So we have a winter formula, summer formula, but that's about it.
Okay, so the knee jerk is to change the composition, but in most situations, it's going to be just to look at the cooling rate. Is what you're saying?
Well, if you look at how a bottle is formed in the IS machine, there's many functions going on there, and like I said before, contact time and what the metal temperatures are, because you can crack the molds open early. There's reheating going on for the transfer of the perishing from the blank mold side to the final blow mold side, and those are all variables that can influence things. So.
Okay, we're down to our last.
Yeah, look, one other thing on the furnace. The other thing I'm having a really hard time with is the requirement that the furnace being operated irregardless of its pull rate to have a constant exit temperature.
Oh, okay.
And the problem there is we have forgotten that there is a forehearth for each production line that allows us the final temperature reduction to get to where we need to make the gob. And we forget that the furnace is going to have variations in pull rate and variations in temperature, but it goes into another chamber called a working end or distributor, and we forget to look at the capabilities there to that being a buffer between what we need to do in the melter for its role in making good glass efficiently, energy-wise, et cetera, versus what is required in a fixed forehearth. Forehearth has its own limitations. So we need to focus more on letting the working end distributor be a buffer between the two. And that's an area that we need to do a better job.
So is the tendency to try to really adjust the forehearth or really adjust the melter that people do? But you're saying the working end would be
Well,
better.
the problem right now that I hear in a lot of factories is the production department says, well, I just want you to have a constant bottom temperature in the melter.
Oh, okay.
And basically what that means is that their role in the operation with the forehearth, which they're responsible for, are basically operating on manual or almost manual. They're not responding or using the capabilities they have to do their own work, especially in the working end, to get that temperature reduction between the throat temperature and the forehearth entrance area.
So I think what I'm hearing you say is don't mess around with the melter so much as let the working end and the forehearth do its own thing in terms of getting the temperatures to where you want them to be.
Well, yeah, I think people handle the forehearth part pretty well. It's just we keep forgetting that we've got this working in there, and there are a lot of capabilities that can be built in there to either help a lot with extra temperature reduction or maintaining of temperatures that would be lost without doing something extra.
Okay. All right, here's the last question. This is Phil Ross predicts the future. So what, if any, disruptive furnace technologies do you see on the horizon that maybe they're starting to arrive, but you think might really take place within the next 10 years?
Well, I think one that's going to have to take hold more that we've sort of made passes at in the past is more waste heat recovery. Some of that has been attempted in the past with preheating of the batch and color going in the furnace.
By regenerators, you mean?
No, by taking the waste heat that as it exited the furnace in the process of combustion gases,
Okay, right.
and using that as a source to get a head start on the batch temperature instead of being ambient temperature, maybe as much as 900 to 1,000 degrees Fahrenheit going in the furnace.
Okay.
And this can be done with preheating of colored only or batch and colored or batch only. And you know, you said I can't use names, so I won't, but a couple of the most energy efficient traditional furnaces in the United States have batch color preheating. And that's been the way they've gained something there. There have been many efforts to look at alternate ways of making glass. We've had electric arc furnace type activities. We've had furnaces that would inject the batch in a flame and try and capture the very hot particles and let the reaction occur very quickly. The majority of those efforts, fluidized batch preheating, there were trials done there. The majority of those were deemed not successful for a variety of reasons. One of the biggest problems that we have, and I for the class I pulled up the history of the natural gas pricing the last 20 years, and it's very cyclical. And so when gas prices go up to over $10 a million BTUs, you say, gee, we can have research and investment and equipment to save energy because it's justified based upon the value of those savings. And then we come into another cycle like natural gas fracking, and the prices go way down, and you can no longer justify the investment because the value of saving has dropped so much. And ironically, right now, I was surprised at this, that the gas price is actually pretty low right now. Not sure why.
Yeah,
because
I don't know.
I'm sure paying a lot for the gasoline in California right now.
Well, that's another story.
Yeah.
I was wondering, I saw an article recently about I believe one of the European companies has made an all-electric container furnace. Now, this is all part of the no-carbon type of push, but I'm not sure how you think that might work out I know that their electric furnaces are common for relatively low tonnage, and things like borosilicate glass in the pharmaceutical industry, they kind of can get away with those sorts of technologies. But I wasn't sure what you thought about for something that's usually is higher tonnage, like in the hundreds of tons per day category.
Sure.
If that can work out, or what that looks like.
Yeah, sure. And I do have experience in this area. I've operated coal top electric furnaces when the manufacturer I was in, and I've worked with them as a
It's
consultant.
called a cold top electric furnace.
Yeah, the true coal top furnace means that 100% of the melting energy is being generated inside the basin of molten glass by electrical equivalent current passing through the glass, and so the batch is put in and it floats on the surface, and it's completely covered. So it's a cold top. It's referred to as
Oh,
a
I see.
blanket, and you can put your hand on that blanket with molten glass, just a foot away, and it's a very good insulator. But all the heating.
I'd let you go first.
Yeah. These furnaces have been used for container glass. In fact, back in the 70s, when we were told we were going to run out of natural gas, a lot of people went into looking ahead and going with electric furnaces, cold top. And then the glow top is one where you may have a certain amount of fossil fuel above the melt, but still 90% of the melting energy comes from electricity. The problem with the electric furnace includes a couple things. First of all, other than what a few vendors will argue with me about, the furnace life is limited to perhaps 5 years.
Oh, really? Why is
the throat is a problem? Even with the best refractories, we still have that limitation. The second problem is that there's a limited turn down ratio. At maximum pull rate, you have a good thickness of batch representing enough glass that you're making each day. When you go down to 40% of the rated capacity, you're putting less batch in, and you lose that insulation factor with less batch present.
Oh, I see. So you don't have as much. You can't adjust the tonnage very easily. Is what you're saying?
You're in a more limited range.
Okay.
Yes. And then the other big issue is the fact that the evolution of gases out of the carbonates, as example, are very easy in a conventional furnace. They're right near the flame and the hot region, and all the CO2 is just going to come out very easily. But in a cold top electric furnace, all the CO2 releases down lower at a layer of mushy glass, and as you have a change in how much gas is being released, excess gas release can make a foam that becomes an insulator, and you have a runaway condition between the glass getting hotter but not all that heat getting to
I
melt.
see.
And this most commonly occurs with reduced glasses like amber, reduced greens, and when we have high amounts of recycled color, which has inherent high organic content, which will trigger additional gases coming out of glass.
Okay. So that may not be something you think that it's going to be hard to implement on a wider scale. Is what you're thinking.
Yeah, I think the trend right now, I think, is driven relative to CO2.
Sure.
Customers are saying, hey, we want to be buying a more green container,
Right.
not just a Heineken beer bottle green type of thing. And so the efforts are being, and there's a cost relative to CO2 emissions. We have cap and trade in California as an example, where there's a financial incentive to reduce CO2. So a couple of things are going on. First of all, a higher percentage of the energy being used as electric is one thing being pursued. And the other is substituting hydrogen either partially or completely for natural gas, because the hydrogen combustion is not going to have any CO2 emitted. And there's been some interesting trials. I've got a picture showing the absence of a flame compared with a natural gas flame in an operating furnace in Europe, where they've run trials for weeks at a time. And there's still a lot to be learned, but there's no question there are ways that we can use hydrogen combustion as an alternative to natural gas combustion. A number of downsides include what type of hydrogen we have. I didn't realize until I got into this a year or two ago that there are different colors of hydrogen, and I didn't.
Different colors?
Well, by designation.
Oh, okay.
And so the greenest hydrogen.
Oh, I think I see what you mean.
Means that you start off with water.
Right.
And by electrolysis, you use electricity that's generated from renewable sources, including nuclear. And then the more traditional way of making hydrogen right now is to take natural gas and split the hydrogen off.
It off of there.
And so the question is, where does that carbon go? And so that you may have a brown or black hydrogen in that category.
Right, so they've assigned kind of
and cost is a big issue.
Virtue categories for hydrogen colors.
That's right. That's right.
Okay, well, I think that that's all I wanted to ask you. Do you have anything you wanted to close out and saying? Or
no, obviously, I appreciate this opportunity to get together and talk a little bit about this. Kind of going back to the ideas to help people out in the future. I think what you want to do is always be learning. Look at the sources of learning. It may be the literature. It may be the people you're working with, the conferences that you can go to, the published papers, et cetera. And try and break down the nostrums of incorrect assumptions that we still have a lot of today, and try and find resources that can give you this information. Because I know in my case, I think about how many things I learned the hard way.
Right.
That it's sure great to have a mentor or means by which you can accelerate the learning process, even though you're now attached to a production operation, which doesn't always give you the time to do some of that. So.
Sure. Well, thanks very much, Phil. We appreciate you being able to step into the studio with us. I'm glad that we were able to catch you here on your trip to Pennsylvania and fit this in. If you are interested in taking a class, maybe you're in the glass industry and you want to, or maybe a raw material supplier, we have some of those at our course today, or people who work in just making the equipment for glass plants, this might be of interest to you. We offer typically yearly either a batch and furnace seminar or an advanced batch and furnace seminar with Phil coming here. And Phil also does other training opportunities in other venues, pretty much, I think, around the country sometimes.
Yeah, and we've done this specific to the course presentation that was developed for AGR here, and we've done that on site when more individual employees can attend, assuming they're not taking away from their regular job. And so we've done that sometimes during furnace rebuilds.
Sure.
When everyone can attend the class for.
So if your furnace is down, it's a good time to get some training. Thanks very much, Phil. Appreciate your time.
Okay.
And
appreciate it.
This is American Glass Research's Breaking It Down. Hope that you would join us next time.